Swayam Prabha. Digital India. Educated India.
Welcome to Introduction to Machine Learning. Today's lecture is going to be going into applications of machine learning, specifically in my area of research, which is diagnostics for precision medicine, for oncology, for cancers. And I will show you how we use machine learning for different problems within this realm, and how it helps bring more precise diagnosis for cancer treatment. So when we think about cancer treatment, it's not just a single shot treatment. There's an entire management of cancer, right from the time of detection and diagnosis to deciding what therapy to give, and then monitoring whether that therapy has been able to cure the cancer, and if not, then changing therapies and following up with the patient. So there's an entire cycle of that, and hopefully the patient comes out of that cycle without any traces of cancer left, and they are able to live on for several more years and so forth, a healthy productive life. So for that, a lot of tests are done at different stages, including imaging tests, which is my area of research, where I develop machine learning and deep learning algorithms for imaging based tests. So if we start from the very beginning, basically we can think of early detection, which is diagnosis, and during diagnosis there are several imaging modalities that are done. For example, MRI, mammograms, biopsies, chest x-rays, ultrasound imaging, and so forth. So based on that, the diagnosis is done about whether cancer is present or not, what is the size of the cancer, what is the stage of the cancer, which means whether cancer is localized within one organ, or has it spread to nearby lymph nodes, or worse, has it spread to distant organs. And based on that, the staging of the cancer is done, and then a tissue from the cancer is extracted, and it is prepared into a microscopic slide that is seen under the microscope, which is the biopsy. And once you see it under the microscope, we can see that the cells have become chaotic. They don't no longer look normal, and they look as if these chaotic cells are invading into the nearby tissue. That is signs of cancer. And based on how chaotic and how disorganized these cells look, we can grade the cancer. So grading means how aggressive the cancer is. And once we have done that, we would be interested in something called neoadjuvant therapy. So one of the primary treatments for most cancers is surgery, where the solid tumor is removed. There are other tumors for which surgery is not possible. For example, cancers that are not solid tumors, or cancers that are in organs where surgery is not recommended. But in many cases, the surgery is the main treatment for cancer. But sometimes the cancer may be too big, and some chemotherapy is given before the cancer. That is called neoadjuvant therapy. So it's either chemotherapy or radiation therapy, or hormonal therapy. So this happens before surgery sometimes, for large tumors, to shrink them before the tumor is operated upon. So once neoadjuvant therapy is given, there is assessment of treatment response. So what that means is that we want to be able to see whether this therapy, neoadjuvant therapy, has shrunk the tumor, and whether now the cancer is operable. So for that, we might do something along the lines of MRI or a mammogram, and then after that surgery is performed, so then the surgical section, the removed tumor, is also again prepared for microscopic slides and seen under a microscope, that is surgical resection pathology. And based on that we find whether there is any disease left, and whether there was response to the neoadjuvant chemotherapy or neoadjuvant therapy in general. So once an assessment is made, then further treatment can be planned, which is adjuvant therapy. This again gives us, there could be different ways of doing adjuvant therapy, such as chemotherapy. Chemotherapy basically is a poison against fast growing cells, and cancer cells are fast growing, so it will go inside the body and kill the cancer cells, but the side effect would include that it will also kill naturally occurring fast growing cells, such as the hair follicles, bone tissue and so forth, so which causes problems such as hair loss, and it causes a lot of other discomfort and side effect among patients. So once that adjuvant therapy is decided, this could also include radiation, it could also include immunotherapy, which is now becoming another more feasible therapy for cancer patients. And based on that we would want to follow up on the patient to see whether the overall therapy has been going on well or not, using PET scans, MRI, and then again resections. So here if the tumor comes back, then we go through the cycle again, but hopefully if we catch tumors early through early detection, then we have to go through this cycle only once. So as you can see that imaging plays a very critical role in assessing, in early diagnosis and assessing the size and grade and stage of the tumor, as well as following up on whether the treatment has been successful or not. So with an image, there are several image analysis problems that can be tackled using machine learning and deep learning. The most basic of these is classification. So let's say this is an image, and this happens to be a CT scan of the chest cavity, of the lung cavity, and here the classification could be simply to classify the image into whether it has a calcified nodule or it does not have a calcified nodule. So that could be binary classification decision. If we want slightly more advanced analysis, we might want to do object detection, which means that mark the areas where you see the calcified nodule. If we want to do even more advanced analysis, we might want to do semantic segmentation, where we highlight the pixels that have calcified nodules, and finally instance segmentation, where we highlight each nodule separately even if they may be overlapping or touching in some images. So these are different hierarchies of image analysis problems for which we might use machine learning. So as some of you may be aware that there is a data set called ImageNet, and the data set was collected by Fei Li and her colleagues to basically foster research in image classification. This data set has 1,000 categories of everyday objects such as cat, dog, car, bus, truck, etc. And initially it had just around 1 million images for these 1,000 categories, and the computer vision community and the machine learning community competed on getting better and better accuracy on this data set. And then starting around 2012 or so, deep neural networks were used on this data set, and then there was a significant improvement in accuracy for this data set. Then around 2014 and 15, the machine learning models or the deep neural network models started to do better than human accuracy. So what does doing better than human accuracy mean? That these data sets, these images have been collected by people who know what the image represents, and when you show it to a person who is not aware of how the image was taken, they sometimes make mistakes. So if you look at an average human, then they sometimes make mistakes. So for example, if you imagine a dog and you take a image from the top view, it might appear like a sheep from the top view. So sometimes in certain angles, or sometimes there are categories that are very close to each other, for example grey wolf and a husky dog, Siberian husky. So then it is hard for non-experts to tell these two categories apart. So based on that, human level accuracy was at a certain level, and in 2014 and 15, machine learning models started to exceed that accuracy. So this does not mean that we have general intelligence in machine learning yet. It just means that if we narrow down the problem in a very focused manner, and we prepare the data sets very carefully, and we create large data sets, then there is a possibility that the machines would start to do better than an average human. And the same kind of thinking can be applied to cancer diagnosis, where if we narrow down the problem very much, then we might be able to start to do better than average human, or even average doctor in that case. So I spend a lot of my time working with digital pathology images, and the way digital pathology works is that initially you would actually take the tissue out from the body, and you would slice it very thin using something called a microtome, and then you would prepare the tissue. So before that, you would prepare the tissue by using formalin fixation, and you would embed it in paraffin, and then you would cut it. And then there are certain dyes that are put, because the very thinly cut tissue is translucent. You cannot really see the structures of cells and tissue very well in that. So the most commonly used dye combination for these tissues is hematoxylin and eosin, which gives us the characteristic pink, blue and purple color. So that is not the natural color of the tissue, it's actually based on hematoxylin and eosin. So once that slide is prepared, it would be actually put in a microscope, and if multiple doctors want to consult each other, then there would be a multi-headed microscope like this, where they would look inside the microscope at the same slide and give their diagnosis. Now instead of that, there are new machines that are being used, which are called whole slide scanners. You put the slide in it, and it will create a gigapixel image. Gigapixel means it's very, very large. It's 1,000 times bigger than a megapixel image. Here basically your each pixel can represent around a quarter micron by quarter micron of the area on the tissue. So that gives it very large pixels for a glass slide, which is roughly 1 inch by 2 inch in size. So you can think of you are getting now 100,000 by 200,000 pixels in a single slide. So once these large images are created, now a simple thing to do would be to now look at these images on a screen. And earlier there was a resistance that the same level of diagnosis that you can do on a microscope cannot be done by looking at the screen. Then certain companies did experiments to show that there is no difference in diagnosis quality if you look at a screen versus if you look at a microscope, provided that it is in good conditions, where there is no strong lighting that is making the screen fade in comparison and whatnot. So now these images can be seen by multiple doctors at different locations. They don't have to come to the same microscope, and it can be stored much better in a digital archive as opposed to an archive of glass slides. What we are more interested in is basically looking at these images and developing machine learning, deep learning algorithms, and based on that we can give an automated diagnosis which can be audited by a human expert. So what kind of classification or regression problems can we create using these slides? So here are some examples. The most basic one would be to classify between malignant tissue and benign tissue. So benign tissue has no cancer, whereas malignant tissue has cancer. So if we can create a large data set of malignant tissue examples, image examples, and then benign tissue image examples, then we can train machine learning to classify between these two, and we can validate it on new data to see whether it is really working, just like we would do with any other machine learning problem. Similarly, we can do grade classification, so whether the cancer is more aggressive versus whether it is less aggressive. Then we can look at different subtypes of cancer. So for example, in breast cancer there is ductal cancer, invasive ductal carcinoma, which is more dangerous, and there is ductal carcinoma in situ, which is less dangerous. So their appearance is different on the slide, and if we mark the areas carefully about that show ductal versus in situ carcinoma, invasive versus in situ carcinoma, we can actually train machines to classify between these two. Now up till here what we were looking at was what a doctor can do, and we are trying to basically emulate what they do when they look at the visual patterns of pathology images, on pathology images. Now we are in the bottom three examples, we are going into the realm where doctors cannot make a confident decision. Perhaps some doctors can, but they cannot describe it easily to their apprentices to transfer that knowledge. So using just HND stained slide, can we detect specific mutations in cancer? Because if you find certain mutations, the treatment can be tailored for that particular mutation for a more effective cure. So there is evidence from different research groups and our own group that you can take, for example, HND stained slides of lung cancer, and you can detect EGFR mutation versus non-mutant or wild type tissue, even if it has lung cancer, with a high degree of accuracy now. Now why this is important is that the traditional way of detecting EGFR mutation would be a more expensive modality such as a DNA testing or RNA testing or something called IHC, immunohistochemistry. Immunohistochemistry is not very accurate, but the DNA testing, once we do expensive testing, we can create a data set where the label comes from the more expensive modality, the training label, whereas the actual image is prepared in a very inexpensive manner using, for example, hemotoxin and eosin staining. And once we have that and we can train and validate the model, we just need HND stains to at least do the screening for the mutation, if not give the final diagnosis for the mutation. So this is something that a human expert will not be able to do very well by just looking at an HND stained image. Now we can go further and we can actually say that if we look at platinum based chemotherapy, then for a particular cancer, will the patient respond to this chemotherapy or not? So we can look at treatment responders versus non-responders, and we will, if we can predict that, where the data will come from past patients and 5 years or let's say 3 years or 5 years of follow-up with those patients after the chemotherapy was given to them, then we can create a data set that will be able to predict what will be the future course of the disease for the patients that we are seeing now. But this has to be validated very rigorously because people's lives are at stake. So it is not an easy process as just running some experiments in the lab. It requires a lot of inter-institutional collaboration to actually rigorously validate it and to get the stamp of approval from whatever is the government body in a particular jurisdiction. So once we have that, we can also go further and try to build models on the lines of regression to predict short-term versus long-term survival and intermediate survival among cancer patients. So before the advent of deep learning, the traditional way of working with medical images was that we would collect the images, we will do some pre-processing to remove variations between different images such as contrast normalization, etc. And then we would extract handcrafted features such as texture features from radiomic images, from chest radiographs, etc. And then we would use machine learning models. We will select some machine learning models, we'll train and validate them. And then once we have done that, we will do some post-processing on the results. Now with deep learning, some of these steps have been condensed, but each step has become slightly longer. So for example, now we select standard architectures such as ResNet 50 or Inception V3, and then we can fine tune them after they are already pre-trained on a large data set like ImageNet. We can fine tune the last few layers or the entire network on the particular medical domain on which we are training them. Now these experiments take a long time and they require a lot of data. So now I'm going to go into challenges that we face in even implementing what seems like a simple approach in deep learning. So before that, let's look at how large these networks are. There's a very popular network called VGG16, which was proposed by a group in Oxford, and their architecture is such that it has 14 million trainable parameters. So if you are trying to fit a equation of a line y is equal to w1x plus w0, it has only two parameters, w1 and w0. This particular model has 14 million parameters, and then the floating point operations in a forward pass are in the order of billions, and then in a backward pass they are even further, much more than that. So the architecture of this VGG net is not actually quite, it's not quite deep as some of the modern networks, yet it has a lot of parameters. So it has a lot of, a few convolutional layers, then a few fully connected layers, and then the final layer is the classification layer. Now with ResNet 50, for example, now there are 50 layers instead of 16 layers and so forth in modern networks. So the challenges that we face when we apply these deep neural networks to medical images are that the image sizes are much larger. In a typical image size for an image taken from ImageNet is around 300 by 300, which is sometimes reduced to 224 by 224 for these networks. Whereas, like I mentioned, for pathology, the images could be very large, as large as 100,000 by 200,000 pixels. Even with radiology, images can be very large, such as 4,000 by 4,000 pixels, and we cannot feed the entire image in one go. If we shrink the image, then we lose a lot of details. So one of the ways around it is to chop the image into sub-images and use each sub-image as an independent image. So now the other challenge that we have is that the number of patients that we get in any given medical study is not in millions. It's usually much smaller than that, a few hundreds, if we are lucky then a few thousands. So the number of images and patients and labels are going to be small in a medical data set. Then we don't have certain invariances in medical images that we enjoy in consumer photography. For example, there is no scale invariance. In consumer photography, your subject could be closer to the camera or further away from the camera, so there is some scale invariance there. Whereas in pathology and radiology, images are always taken almost at a fixed distance from the fixed effective distance, let's say, from the sensor of the camera. So because of that, we don't have scale invariance. And then if you think about chest x-rays, you cannot really rotate them and still call them a chest x-ray the way we can rotate certain objects in consumer photography. And then there is also no translation. The chest cavity, the lung cavity always appears roughly at the same position. The heart always appears roughly at the same position. And then we also have a lot of imbalanced classes. There are conditions, medical conditions that don't have a whole lot of patients. For example, we may have a lot of normal patients and very few cancer patients if we do a screening in the population. And because of that, we have to constantly deal with imbalanced classes in medical studies. The image characteristics of these images are different from consumer photography. So the low level features that a convolutional neural network extracts may not be the same between what is trained on ImageNet versus what is trained from scratch on one of the medical image modalities. Then we may have uncontrollable data characteristics, which means that we may train machine learning models from one hospital, and when we want to apply it to images from another hospital, we may see that the model does not work very well because the data characteristics have changed. The reasons for those changes could be as myriad as change in the equipment. Even if the equipment gets better in the other hospital, the machine learning model has not seen data from the new equipment, so it doesn't work very well, doesn't generalize very well to that. It may not generalize very well. Other issues could be that the patient characteristics have changed. We may see early stage cancer patients in one hospital versus late stage cancer patients. Different ethnicities may have slightly different changes in how the underlying tissue looks, or because of comorbidities such as pollution and smoking, we could have a different looking tissue. And then of course there are concerns about privacy and regulations while working on these studies. The deep neural networks and more complex machine learning models, their decisions are quite opaque. which makes it uncomfortable for doctors to use and trust these models, and rightly so, because it has been shown that sometimes a very benign looking change in an image, for example just having an annotation of some letter in the corner of the image, can change the outcome of that image when processed through a machine learning pipeline. So these models have to become more and more transparent if we have to drive the trust in these models. Speaking of trust, we also want to make sure that the confidence of these models in their decisions is calibrated, in the sense that if the model sees a kind of image or a data that it has not seen before, then it should not make an overconfident decision. It should still make it should be able to recognize that this is an out of distribution data, and based on that it should be able to calibrate its confidence downwards. And of course the experimentation times are long, because these neural networks take a lot of computation to converge on the solution. We have talked about stages of the AI life cycle before, and I will quickly revise that we spend a lot of time in data preparation and training and validation in machine learning courses, whereas there are other considerations to be kept in mind, and more so for medical AI or diagnostic AI. So we have to start with the right economic need, whether making this predictive model will actually makes sense in terms of healthcare outcomes and so forth. And then we have to think about whether what kind of a model will actually help us achieve that economic goal. Then comes the stage of data preparation, whether we are collecting data in a cost effective manner, whether we are collecting it ethically, whether we are collecting it without bias, and so forth. And after that there is training and rigorous validation, where we keep in mind the scenarios in which the technology will be deployed, so that we get as close to that deployment scenario as possible when we validate the model or test the model. And once we are done with that, we will package and deploy the model within some software or hardware system. And at that time we want to make sure that the user understands what the model was trained on, what it was meant for, and how it is to be used. And then it is still not fire and forget, especially in medical imaging. We should put in place a system to monitor and audit the AI technology going forward, and catch any changes in its behavior early on before it can give suboptimal decisions for people that will be most affected by it. In terms of validation of AI models, the validation has to be quite rigorous, and that rigor can keep increasing depending on how far we want to take that validation. The most basic one is that we should do a patient level separation of training and test data, which means that if we train on a patient A, that patient A should not be used for validation or testing, even if it is a new image for the same patient, because AI models can easily give high accuracy by latching on to patient specific features as opposed to disease specific features. So the least we can do is make sure that the patients do not overlap between training, validation and testing. And if you want to make it more robust, the validation more robust, then we would also want to separate the training, validation and testing by hospitals or by populations. By populations I mean that a model could be trained on Chinese population and tested or validated on Indian population, so that we can also make sure that any comorbidities and any underlying genomic differences, is slight as they may be, those are also generalized over. We make sure that is done when we apply the same model to a new population. Then the data acquisition setup should also be tested for generalization, which means that if we train on images taken from instrument A and instrument brand and model B, then they also work on model C before we roll it out. So when it comes to the overall predictive modeling using machine learning in medicine, it can be organized in the way that is shown in the image here. So we can start from any data that is on the left hand side and try to predict something that is on the right hand side. So for example, we can take clinical data and imaging data and try to predict what is going to be the molecular data, which is the genomic test or the the mutations that are present in a particular cancer. We can take it further and we can say that let's try to predict the precise diagnosis based on the data, these 3 data points that we have on the left hand side. And then we can even combine it with treatment data and let's try to predict the outcome now, which is the holy grail of medical image analysis using machine learning. So we can do things such as morphological classification, staging and grading, molecular status determination, treatment planning, and biological understanding. So now let's go into specifics of some of these techniques. We will talk about how to replicate human expertise for some time. Then we will talk about how to go beyond a human expert. Then we will get into overcoming real challenges with medical data. And then we will get into uncertainty estimation in AI, and then look at some other applications of AI that I and my colleagues have been working on. So when a woman gets breast cancer, not only do we take a tissue from the cancer and stain it using hematoxylin and eosin to see whether there is really cancer or not under a microscope, we also do some molecular tests so we try to detect certain proteins that can help us choose the right treatment for a particular cancer. One of those proteins is the HER2 protein, and to detect that we use immunohistochemical stain, IHC stain called HER2/neu. This particular stain, when it is put on the tissue, if the tissue has HER2 protein coming out of it, it will stick to the membrane, and based on that it will give you this complete brown circles around the cells that have HER2 protein on their membrane. So you can see that this complete circles that you see here is a sign of HER2 positiveness, and same here in this other image. Now on the other extreme we have almost no brown stain that is present in HER2 negative patients, and then we have intermediate scores such as 2, HER2 score of 2, where we have some staining but it is not like a complete circle around the cell membrane. Now this is a non-trivial problem because we cannot just go into detecting the extent of brown color and make a decision based on that. As you can see that this extent of brown color is much more than this particular color, yet this is a HER2 negative and this is HER2 intermediate. Here again we have a lot of brown color, and here we have less brown color, but the membrane is better circumscribed in this image as opposed to this image, which makes this as HER2 positive and this one as intermediate HER2. So a person who has a HER2 positive breast cancer would be given special treatment, which is anti-HER2 treatment, that has improved their survival chance before compared to before these treatments were actually starting to get used. So my students worked on a competition to detect HER2 positivity in breast cancer IHC images, which was organized by University of Warwick, and what they did was they encountered these tissue images where not only the patient image was given but also a control tissue was given which was known to be HER2 positive. So if we can somehow use the control tissue, that helps us improve the results on the patient itself. So what they did was they looked at the H&E image that had no control tissue. They matched the shapes with those in the IHC tissue. The unmatched shape, they inferred that as a control tissue to automatically detect control tissue, and then they extracted colors from the control tissue and gave it as a separate input into a neural network, a convolutional neural network. In a convolutional neural network we would have convolutional layers, then we would have fully connected layers, and then we would have the output layer. So somewhere between the convolutional layers before the first fully connected layer, they actually inserted the brown color that was extracted from the control tissue, and which gave uh, uh, their model an edge over all the other competitors, and they got the highest accuracy in that competition. So much so that when compared to the results of a single pathologist, their model was more accurate than a single pathologist. That is not to say that the role of pathologist is ending. It is just that now these tests can become a feasible force multiplier for a pathologist, where they can automate these tests and then actually uh, take their job to be that of a supervisor of AI, as opposed to doing the work that AI can already do. So this is an example of given a tissue slide, what kind of mapping their neural network can do, with different colors represent different grades of HER2-ness, and when we mine patches from that, we see that indeed this looks like that it is HER2 positive, whereas these areas look like that they are HER2 negative. Then we realized that just extracting color from a particular tissue and inserting it somewhere in the neural network may or may not work all the time. So how can we actually do color normalization, which means that given a particular tissue from one lab, and let's say the machine learning was trained on tissue from another lab, we can see that there are slight differences in appearance of the colors because of the scanner response or the batch of chemicals that was used to prepare the tissue. So how can we make this tissue look like this in color without actually changing the structure of the tissue itself? So for this we use something called non-negative matrix factorization, which is similar to principal component analysis with some differences. In principal component analysis, we are reducing the dimensions of the data in an unsupervised manner, and what we are also doing is that we are assuming that these principal components represent some underlying latent representation in the data. Now what if this data is always positive, always non-negative, and the way it mixes with each other is also using non-negative coefficients? That's where non-negative matrix factorization comes in. So we use non-negative matrix factorization for rank reduction, for dimension reduction in such cases, and it gives slightly better results than principal component analysis. So we took these images, we converted them into optical density by taking a log transform, and after that, on the optical density of red, green and blue channels, we computed a dimension reduction using non-negative matrix factorization into hemotoxylin and eosin. So from 3 dimensions we took each pixel and made it into 2 dimensions, which is how much hemotoxylin or how much eosin it is absorbing. We also put some sparsity constraint. You are familiar with L1 regularization, so that's exactly what we used, so that each pixel is either has hemotoxin or eosin but not both, or it tends to have that. So their coefficients are going to be sparse, some of the coefficients are going to be 0. So once we were able to separate the hemotoxin and eosin for these images, we took the coefficients of the original image but the color basis of the target image. So you can think of the color basis as the principal components, whereas the eigenvectors, and you can think of these as the coefficients or the projections along the eigenvectors. So we combined the two, and based on that we got a new representation where we took the inverse log transform or the inverse Beer-Lambert transform to reconstruct the image. So you can see that even if we could have replaced this entire step, instead of sparse non-negative matrix factorization, we could have replaced it with PCA, principal component analysis, and the logic would have been the same, and indeed previous researchers have used PCA, just that we got better results with sparse non-negative matrix factorization. Then we further improved upon these results by also making sure that images, pixels that look similar, their deconvolution into different components of hematoxylin and eosin, those are also closer. For that we use something called graph Laplacian regularization, where we took the difference between different input vectors, which is the optical density of red, green and blue channels, and then we constructed a graph of nearness of each pixel with every other pixel based on how near the colors were, and based on that we made sure that two pixels that were close in color space, their hematoxylin and eosin were also close to each other when we did the non-negative matrix factorization, and based on that we got slightly improved results than our previous technique as well. And those improved results can be seen here, that this was using sparse non-negative matrix factorization. We miss out some tissues during reconstruction, which we can construct much better using the graph regularized sparse non-negative matrix factorization. Then we found that these techniques that we developed, they were quite slow, and that is because a lot of these packages are not optimized for GPU computing, whereas after the color normalization we are going to use the GPUs anyway for training deep neural networks. So why not actually do the color normalization as a first stage in a deep neural network itself. So we repurposed a deep neural network where we took the original red, green and blue channels and computed what needs to be added to those channels so that we can reconstruct a color normalized version of that image, and that we trained using several input images with one target image. And then what we could do is we could take this network and use it as a pre-processing step in a task specific neural network, and we got improved results with that. Then another thing that we can do in computational pathology is to detect all nuclei of cells and use those to actually study what is actually going on in the cancer and the immune response to the cancer, for example. So what we can see here is these are different nuclei in these images, and these are very crowded nuclei. So if you see this complete circle here, this complete circle is one nucleus. What you can see is that it is like overlapping with another nucleus right below that and right to the right side of that and so forth. So for a regular image processing algorithm to detect these as separate nuclei is not easy. The other challenge that you see is that these nuclei have these are uneven in color. There is a dark boundary and there is a white portion inside that. If the nucleus was as simple as this particular nucleus, where it is dark and uniformly colored and isolated from all the other nuclei, then it is easy to detect such nuclei, but not so for other nuclei that I showed before. So you can see that even something as simple as Otsu thresholding is able to detect these nuclei, but then all the other nuclei get merged together because they are overlapping or they have uneven color. So here we were able to do a much better job of detecting them using a deep neural network. And the trick that we used was that before this deep neural networks used two classes, which is background and foreground. So foreground would be a nucleus, background would be a non-nucleus area, but that doesn't take into account when the two nuclei are touching each other. So we defined a third class, which is the boundary class, which is what you can see here, that we are predicting the boundary using neural networks. We annotated 20,000 nuclei by hand, and based on that we trained the neural networks, and we showed that on unseen images, even unseen organs, we were able to get very decent separate instance segmentation, multiple instance segmentation of these nuclei. So I will show you the result here. So you can see that several of these nuclei that are very uneven in color or overlapping with each other, those can be very easily detected using our solution. Since we had put in the effort to detect so many nuclei, what we did was we put our data set on the public domain, and we organized a competition in one of the research conferences, MICAI 2018, and we encourage people from all over the world to use our data set and improve upon our technique. And indeed several research groups from around the world, they rose to the occasion and they did slightly better than our original technique in detecting separate nuclei from multiple organs, including organs that were not disclosed to them during the training data, in the training data. We also propose a new metric for evaluating such outcomes so that we can do apples to apples comparison between different techniques using our data and a single metric. That metric that we proposed was, we called it aggregated Jacquard index. Then we proceeded to say that why not even detect not just nuclei themselves, but what type of nucleus it is, what type of a cell does this nucleus belong to. So epithelium is where a lot of cancers originate. So all these epithelial cells are usually cancer cells in the images that we were working on. And then there are 3 different types of cells that we wanted to detect from the immune system itself. So lymphocytes, these are largely white blood cells that attack the cancer, or sometimes the cancer repurposes them to serve its own agenda. And then there are macrophages cells that digest the cells that have been attacked by lymphocytes. And then there are neutrophils which also play a important role in the immune response. So we hand annotated these 4 types of nuclei, around 40,000 of them, and we launched another competition for people to develop their techniques based on our annotations, and several of the research groups did quite well on this data set, and we just closed the competition last year. So now you can see that machine learning is start to do these low level tasks of detecting something or segmenting something that a human can also do, but it is very tedious for a human to do. Now let's see how we can go beyond a human expert in making some of these diagnoses even more precise. So if you look at going back to that HER2 positive breast cancers, we can see that a human expert as well as a machine can look at these IHC stained images and they can see that this is a HER2 positive cancer. But this inexpensive image, which is the HND stained image, on this can a human detect whether they can see that this is cancer, but whether this cancer is HER2 positive or HER2 negative. So it turns out that it is not very easy for a pathologist to do that. There are some pathologists who have seen enough of these and they can make an intuitive decision on this, but they cannot teach it to others. So what we did was we actually took paired images. These are usually 2 different sections of the same tumor close to each other, so that we know that it's not the same section but it is close to each other. We can find whether based on some shape matching, whether when we see the brown response here, then this region that looks similar in shape must also be HER2 positive. So based on that, we went back to the images and we hand annotated a lot of these images. You can see that this is HER2 negative and this probably corresponds to these glands here. So these are also HER2 negative. So we marked it with blue color, which is negative. Similarly, this is HER2 positive, this region is HER2 positive. We marked the corresponding regions in this magenta color as HER2 positive, and this is the non-cancer region which is also seen here marked in green. Then we train neural networks to detect the 3 different types of tissue, and for that we actually found that instead of using a single neural network to do everything in one shot, it was actually easier and less error prone to do this in a multi-stage pipeline where we can diagnose the errors of each stage separately. So we had one neural network that detected all the nuclei using the technique I described previously. Another neural network detected all the cancer nuclei, and a third neural network decided whether the cancer nuclei were HER2 positive or negative. So these are some architectures of these neural networks. There's a very famous architecture called the UNIT architecture, which we modified for this purpose. And we can see that the nuclei were detected very well. So this is the same image with the detected nuclei marked in green. And then we extracted patches where the nucleus was at the center, so that it becomes a little easier for the neural network to process it further and decide whether it's a cancer cell or a non-cancer cell, and then HER2 positive cancer cell versus HER2 negative cancer cell. And this is the custom architecture of a neural network that we built for HER2 positivity detection. And finally, these are results on previously unseen images, where we can see that these blue markers put by the neural network show HER2 negative cells, which is also confirmed by the IHC of the adjacent section of the same cell. Similarly, the HER2 positive cells marked by red can also be confirmed to be HER2 positive in IHC, and the non-cancer cells can also be, the green non-cancer cells can also be seen as non-cancer cells in the IHC. We also looked at other types of breast cancer such as basal, luminal A and luminal B, and we trained neural networks to see whether we can detect these cancers and whether it corresponds to whether the determination of the cancers was similar in using the genomic data. Then the next problem that we have worked on is detecting intra-tumor heterogeneity. So we know that cancers are different between different people, even if it is in the same organ. So they should be given treatment that is tailored to their particular cancer. However, even within one patient, there can be different foci or different parts of the cancer that have different mutations. The current treatment paradigm is to treat for only one mutation, one dominant mutation, but then there can be subclonal mutation where there can be multiple subtypes of cancer present in the same patient. There have been several studies that suggest that because of this intra-tumor heterogeneity, ITH, the cancer fails, the cancer treatment fails. So it is important to detect this, and in future there may be trials where we can use a cocktail of treatments that may be able to better target the cancers in these patients. So even when we look at the IHC of HER2 positivity, we can see that although all these three patients are HER2 positive, in this particular patient only a small portion is HER2 positive, rest is HER2 negative. So this could be a heterogeneous cancer. So if you look at these four types of breast cancer, luminal A, luminal B, HER2 and basal, what we can see is that if we have a basal detector by looking at the tissue and see whether it looks like the shapes that you are seeing are basal, then we can have a low basal and a high basal score, and basals would be high on basal and luminal A and B would be low on basals, and HER2 will also be low on basal. On the other hand, if we train another classifier to find HER2 positive shapes, then we can see that low HER2 would represent luminal A and B and basal, whereas high HER2 will represent HER2 positive breast cancers. Now it's possible that we may get intermediate scores for both basals and HER2s, and that could be that these cancers are have intra-tumor heterogeneity. We went ahead with this hypothesis and we looked at the molecular data of HER2 and basal cancers, and we see that most of the basal cancers form one cluster and the HER2 patients form another cluster, but some of the patients that are actually basal can actually intrude into the HER2 cluster, and vice versa, that a HER2 patient can intrude into the basal cluster. So we conjectured that these patients have intra-tumor heterogeneity. So we took them out from training and only trained classifiers, visual classifiers on those patients that fall into one category or the other very clearly. So based on that, we took the whole slide image of these patients and we divided it into small patches, and we trained image classifiers on those small patches. And initially we did not use deep learning. What we did was we extracted something called bag of features. This is based on something called interest point detection and feature extraction, such as histogram of oriented gradients. And after that we trained support vector machines, SVMs, to classify them into basal, non-basal, and another SVM to classify them into HER2, non-HER2. So what we found was that if we look at the probability of basal and probability of HER2, we find the expected behavior that in the test cases the basals turn out to be high on, basal patients turn out to be high on basalness, low on HER2ness. HER2 patients turn out to be high on HER2ness, low on basalness, and luminal A and luminal B patients turn out to be low on both. But we found the same patients that we held out for training because they were intruding into the other cluster, they were somewhere in the middle for both. So for these patients, we were able to detect these patients as heterogeneous patients, and in the future what we want to do is we want to be able to take a tissue and map the pockets of HER2 so that genomic tests can be done better, intertumor heterogeneity can be assessed better, and treatments can be planned better. When we actually look closely at those patches that are heterogeneous but they are designated as HER2 by our computer vision system, machine learning system, we find that they look quite similar to the homogeneous HER2 cancers, and same for heterogeneous basal cancers versus homogeneous basal cancers. Now the surprisingly what we found was that this intertumor heterogeneity has not been very well defined in previous research. So we went out to define it on our own based on a set of 50 genes that are called PAM50 genes that have been discovered before to characterize breast cancers. So we used a established technique called T-SNE to reduce the 50 dimensions to 2 dimensions for visualization, so that we can look at clusters of different subtypes of cancer. We can see that this is a luminal A cluster with black dots, each dot representing one patient, and then we have other subtypes of cancer. We started concentrating on luminal A breast cancers because those have the best outcome, they are more easily treatable. But what you can see is that not all patients are concentrated towards the center of the cluster. Some of them are quite far from the center of the cluster. We conjectured that those that are far from the center are precisely the ones that have intertumor heterogeneity, and they will probably have poorer survival because they have characteristics of other subtypes of breast cancer also present. So to characterize that, we looked at the relative distance from their own center versus the other centers, and we didn't look at just the Euclidean distance in those 50 dimensional space. We looked at something called Mahalanobis distance, named after the Indian mathematician Mahalanobis. What it does is it looks at the directions of variations of a cluster, and it normalizes the distance directions based on the principal component analysis of that particular cluster. So based on that, we looked at all the luminal A cancer patients, which in clinic were all diagnosed as luminal A and treated as pure luminal A cancer. But we found that if we separate these patients into 2 or 3 groups, which is pure luminal A patients versus patients with intertumor heterogeneity or the admixed patients, their survival is very different. On this graph what we show is that how time progresses and what is the probability of survival. So initially everyone is alive, and at a long time on the right hand side everyone will eventually die anyway, including those that don't have cancer. So these curves keep coming down, but how fast they come down tell us whether the outcome is going to be on an average better or worse. So what we can see is that pure luminal A survive better compared to the admixed luminal A, which we quantified using our intertumor heterogeneity metric. Additionally, what we found was that these admixed tumors were more likely to be of higher stage, of larger size, and be present in older women that have undergone menopause, as well as we found that genomically these tumors were more likely to have proliferation genes and HER2 gain and recurrence score. So based on these characteristics, we were able to separate out a clinically homogeneous group into further bifurcation, so that more and more precise ways of looking at these tumors can be devised. Now we are working on the next generation of defining these intertumor heterogeneity matrix using again non-negative matrix factorization, a particular form of that which is called semi-supervised non-negative matrix factorization. And then we are also working on computer vision techniques to mark out the pockets of different mutations within the cancer. Another problem that we worked on was predicting the outcome of a treatment in prostate cancer. So instead of going through the entire stage, grade, etc., what if we could predict whether the surgery is going to be successful? And by successful in this case, we meant that within 5 years the cancer will not come back. So here we made use of a data set that we had from an interinstitutional consortium where we have a matched data set of grade, stage, race and age, which are known to be factors in recurrence. So now once we have a matched data set, each patient that for which the cancer did not occur had a matching patient in the cohort where the cancer did reoccur after surgery with the same grade, roughly the same stage, race and age. So that means we have taken these factors out of consideration and we are concentrating only on what actually seems to appear in these images. So here one of the first techniques that we used was we did image segmentation to find different types of nuclei and different types of tissue segments such as the connective tissue or stroma, epithelium or the gland area which also harbors the tumor and so forth. And then we extracted features, some 6,000 features per image from these images, and then we built models that eliminated a lot of these features by using L1 regularization and fit logistic regression on those models and validated it on held out patients, and it gave us some decent results. Then we started using deep learning where we use multi-stage pipelines. The first neural network just detected all the nuclei using the techniques that I had shown before, and the second one basically tried to see whether these nuclei belong to a recurrent cancer or a non-recurrent cancer, and we got an AUC that was better than if we just use the clinical data on a held out set of patients. Now let's look at how we can overcome some real challenges using more advanced machine learning techniques while working with these cancer images. So let's say we are not able to annotate regions for training neural networks, then how do we work without these annotations, where you can see there's heterogeneity. There is this portion which is the gland portion, but there is also this portion which has no gland, which is the connective tissue. So this does not give us much clue about which of the four conditions it is, whether it is benign or malignant. So how do we train neural networks to ignore these regions and large images? There is a set of machine learning techniques called weakly supervised learning. Here we use a technique by Ilse et al., which is attention based multiple instance learning, and we repurpose it for our problem so that we can not only make the diagnosis correctly, but we can also highlight the regions that the neural networks used to make the diagnosis. So in this weakly supervised learning, the image is broken into sub patches, these block like architecture that you see, these checkerboard patterns, each of them is a small patch of the image, and for each patch the neural network not only computes whether it is malignant or benign, but also computes whether it is important to determine malignancy or benignness. So that importance score is called attention score, and based on the attention score we can dim the lights on those patches where the attention score is low, and you won't see that, so that the visualization only highlights the regions that were important for visualization. We use the same technique for detecting BRAF mutation in thyroid cancer, where it is not easy to highlight the regions where the mutation is present, and we developed same kind of a attention based multiple instance learning that we learned the basics of that from another research, and then we slightly modified it for this particular application, and then we developed a visualization technique which I will show you shortly. But first, even on a held out data set and data set from another hospital, we got very good results in predicting BRAF mutation. the visualization technique basically tells you where the positivity, mutation positivity signal is coming from, which is the red signal, and where the negativity signal is coming from, which is the blue signal, as well as which regions to ignore, which are neither positive or negative, which means they are neither highlighted blue or red. And what we see is that we can actually home in onto the different structures of cell that suggest mutation positivity versus mutation negativity. And some very expert pathologists have suspected that these types of cells, which are called oncocytic cells, are indeed BRAF mutation positive, but that has not been replicated from one pathologist to another. Now with deep learning we can replicate it from computer to computer, because it's just the same model that can be copied into another computer. We also develop multi-resolution techniques for working with pathology slides. Some of the some of the features that we want to extract from these pathology slides are at the nucleus level, the shape of the nuclei, the size of the nuclei, etc. And some of them are at a macro level, where we want to see how these nuclei arrange into tissue patterns and so forth, histological patterns. So we want a multi-resolution information extraction from these images. So there's a very popular architecture called a unit architecture. We use that, but within each stage of the unit architecture, we further extracted multi-resolution features and combined them to get better processing, where we can see that these dim regions that you see, bright pink regions, these are germinal centers in a lymph node. We wanted to extract that for some study, and we can see that if you look at the gray versus the white, that is a comparison of the two techniques, and they are very quite close because we were using multi-resolution techniques. Then we develop loss functions that are very specific for certain applications, that overcome problems such as data imbalance, class imbalance, and so forth. As you already know, that this cross entropy loss is quite well used in classification, especially with logistic regression and neural network type architectures. But Facebook research proposed something called focal loss, where we can slightly modify this cross entropy so that we can work with imbalanced classes. We further modified this for segmentation using something called positive dice loss, which has already been used, but combining it with inverted dice loss, where we treat background as foreground and foreground as background to overcome the limitations of just using dice loss, which means that sometimes when we are trying to, for example, segment nuclei in images where there are crowded nuclei, the foreground is more prevalent. When we have sparse nuclei, then the background is more prevalent. So we can basically switch. We came up with a way to switch between the two losses using a particular criteria, and based on that, our results for segmentation were much better than some of the previously published, not much better, but at least slightly better than some of the previously published results on both MRI, where we are segmenting heart chambers, and on pathology, where we were segmenting nuclei. Then we can also make these neural networks more robust by using different techniques such as adversarial training as well as self-supervised learning. What we can see is that if we know the image and we have access to a neural network, previous researchers have shown that we can do gradient descent on the input, not on the weights, but on the input, to come up with slight variations of the input image which are imperceptible, but that gives very poor results of classification or segmentation on the same network. So you can see that here the segmentation is quite good of this particular chamber of the heart, but with slight perturbation of the image. This perturbation is what was added, but it is exaggerated so that you can see it on the screen. It is actually very slight. It is exaggerated 700 times, and when it is added to the image, we get very poor segmentation results. So we used these adversarial attacks to train more robust neural networks, as well as we use something called self-supervised learning, which has been proposed by other researchers before, where we don't rely on data sets on neural networks that are trained on ImageNet to work on medical data. In fact, what we do is we create a bogus task for a neural network to solve so that it learns the structure of the images. So here the challenge that we are solving is that we don't need very many labels to train neural networks if we have a whole lot of unlabeled data available. So let's say we have a very large data set of chest x-rays which is unlabeled. We can create jigsaw puzzles from that, and because we know how we jumble the various parts of that jigsaw puzzle, we can train a neural network to unjumble it, and in doing so it learns the characteristics of the image so that it can now do the diagnosis, learn the diagnosis with a few labeled samples as opposed to many labeled samples. So based on that, we showed that we can train more robust neural networks that also give us higher accuracy. We also work on something called active learning, where if we have a pool of unlabeled data and we have only a small budget to get subset of the data labeled. So imagine you have 1 million images of chest x-rays, but your radiologist is very busy. You can only give her 100 images at a time, and you can go to her only 10 times. Then which 1000 images and in what sequence should you pick them so that you get the maximum improvement in your neural network? So we need an algorithm to suggest which images to pick to get labeled by the radiologist. So that itself becomes a machine learning task. So here we use self-supervised learning to basically use the conjecture that if we cannot solve a self-supervised learning task on a given image, then that image must be hard for the neural network, and consequently if we get it labeled by the radiologist, we will get maximum new information that will help us improve the neural network. And based on that, we showed that our techniques was slightly better than some of the previous techniques, but more importantly, when we mislabel some of the samples, which will inadvertently happen in any prepared data set, then our technique does much better than the other techniques. And if we introduce new classes, our technique catches up with the original performance within a few rounds of getting the data labeled. And the reason it does very well is because we have this self-supervised learning based query generation, as well as we try to get more diverse samples from the training data set by dividing each query into sub-queries, and that also gives us better results. Then we are also working on modular neural networks, where a large module of the neural network is not trained at all, and only a very small neural network is trained for a new task. The application of this could be on edge devices, where you can have an application specific IC do most of the calculation, but it does not need to learn anything new. Only a small portion can be outsourced to a small GPU on your phone to learn the work on a new task. So the most common technique is that we take the entire neural network and we train it, or we train only the last few layers. Then there are other researchers who suggested these side modules called serial adapters or residual adapters, and we suggested something called adaptive attention adapters, which use even fewer number of parameters to retrain for a new task compared to the residual and the side adapters. Then we also try to understand how these cancer cells and the way they interact with the immune system can, what kind of characteristics of that tumor microenvironment should be visualized to understand these cancers better. So for that, what we did was we looked at these cancers, we detected all the nuclei using some of the techniques I described before, and then we formed a graph of these neural networks, where each vertex in a graph is a neuron and the edge is between neighboring not a neuron, nucleus, and the edge is between neighboring nuclei. So now we have a graph structure, mathematical graph structure, which we can process using a graph neural network, and based on that we can do classification between different subtypes of cancer. And on top of that, we added an attention layer that basically tells us where the decision about that cancer is being made, so that we can do better visualization of the tumor micro environment. So here's an example of a in situ breast cancer where this membrane is not broken, whereas in invasive cancer the membrane is not present. So we can see with our technique that membrane is highlighted automatically because of the attention portion of the network. And between Gleason 3 prostate cancer and Gleason 4 prostate cancer, where in Gleason 3 the complete circles of glands are still present, whereas they become more merged and chaotic in Gleason 4, we can see that our network highlights the gland shapes quite well. So we hope that now that we have confirmed that it works for in situ versus invasive breast cancer, or Gleason 3 versus Gleason 4 breast cancer, we can apply it to new situations where we don't know what we are looking for, and it will highlight the regions for us where we should be looking. Now let's look at uncertainty estimation for medical AI. So as you know that one of the challenges with AI, especially neural networks trained using cross entropy, is that they are quite overconfident even when they are wrong, even when they see new data. So you won't see probabilities that are that should be close to uniform probability when they see new data. So how can we force neural networks to recognize their own uncertainty? You have to train them in a special way. So it should not only tell us whether it is what is the average accuracy, but also it should give high accuracy on certain data and low accuracy on the uncertain data. So one of the ways we did that was we looked at the loss of the neural network, and we modeled the loss itself as a beta distribution, where when the loss is high we assume that these are some of the mislabeled samples or out of distribution samples, and we should not be using them for training further. We should be using the certain samples for training, as well as at test time we can see that these could be the uncertain points. So what we found was that if we look at this loss, those that have low loss are usually informative regions of the cancer, whereas those that have high loss are uninformative regions of the cancer. Here what you can see is that most of it is stroma, which is not even in the cancer region. Consequently, we can also improve the accuracy of detection by using this technique. We also used Bayesian neural networks to get an estimation of survival in cancer using genomic data. So if we input gene data into a neural network, and we put a prior on the weights of the neural network, which is a spike and slap prior in this particular case, and we try to reduce the KL divergence between the output and the actual weights and the spike and slap prior, we can get not only the prediction of survival but also the uncertainty estimation around that. So what that does is that not only improves our estimate, but it also helps us detect when we have a out of distribution data. So for example, if we train on patients whose age was greater than 60, or their survival was low, which is the red curve, but if you look at the spread of the red curve, we can see that that spread is low, because when we tested it on held out older women, then the model was more confident, but when we apply it on the younger women age less than 60, we can see that the uncertainty is higher because the model is less confident, and rightly so. And we can also get an estimation of which features are how much important. So for example, age and lymph node positivity are very important, and then BCL2 gene, for example, is important compared to some of the other genes such as RRM2 gene. Then we also used another technique for detecting uncertainty in cancer images, where what we did was we put a prior on the outputs such that the prior was uniform prior. You get uniform probability when the estimation is uncertain, and based on that, what we can see is that if we train on certain conditions of the skin, we get low uncertainty for the known conditions, whereas when we introduce an out of distribution condition, then we get higher uncertainty. We are also using another approach for detecting this uncertainty. This is something called SIM-CLR, which was proposed by Chen et al. And Siga et al. So basically what they did was you take a particular image, you create its modifications and train a neural network to give similar features for its own modifications versus modifications of another image, and that's a form of self-supervised learning. Now with that self-supervised learning, we can see if two modifications of the same image give similar features, then it must be an inside the distribution image. If they are quite different from each other, then it must be outside the distribution, on which the model should be less certain. So we did another enhancement on that, something called supervised contrastive learning by Khosla et al. We use that for medical images, and we applied it to a colorectal data set, and what we can see is that without using the supervised contrastive learning, what we can get, the separation between out of distribution and in distribution data is not very well, but once we use the supervised contrastive loss, then basically we get better separation. So this brings us to the end of what we have done on cancer image analysis. Let's look at some examples of non-cancer applications of deep learning and machine learning. So there is something called metamaterial, which is basically nanostructures that we produce on silicon that basically give the surface very specific properties such as radar avoidance or particular polarization at particular angles and so forth. So what is done is there are structures like these that repeat on, these are nanostructures that repeat on at regular intervals on the surface of these materials, and based on the shape of these elements, the properties such as optical properties can be quite different. So question is, if we have an optical property in mind, can we figure out what structure needs to be printed on this material? So for that we take a lot of these structures and we simulate their forward model, which is basically predict their use a physics solver to predict their optical properties, and then we use the optical properties to train what the original structure should be like, and when we apply it for new optical properties, we can get a good idea of what the structure should be. Then we have also worked on super resolution, where we look at the image and we try to create a larger image where the details are not blurred and they are sharp and believable. So for that, what we did was we took an image, we assumed it to be the approximate coefficients in a wavelet decomposition, where these detailed coefficients are, we assume those are missing, and these need to be generated using a neural network. So we took the original image, used a neural network to generate the high level details, and then combined the two to get a larger image. Now how we trained this was, we first took original images and we downscaled them, and then because we downscaled them, we know what is the detailed coefficients of wavelet transform of the original images and the downscaled images. So we can do this, build this prediction model, and then we applied it to unseen images and see how it works well. And what we got was results better than simply using CNN directly on images. We were able to get better results using wavelet than compared to simply using CNN directly on images. With this, I come to an end of this lecture on applications of machine learning to various image processing problems, especially in medical domain, especially in cancer pathology. I hope you found it useful and you can think about new ways of applying machine learning to various other domains. Thank you.